Hi everybody, this is Dr. Nigro with a screencast for Chem calculations. This one is going to be an addition to the KEQ screencast that's already been posted. That one dealt with KEQ expressions where everything was aqueous, so we used concentration values or molarity values. But if you have a system that's all gases, you can also calculate the equilibrium expression, the constant, using partial pressures. So I wanted to do a separate video with those types of problems, just so you would have some examples. All right, so when we have KEQ, we can call it KC, and that means everything that we put in is a unit of molarity. Or we can call it KP, where everything is a partial pressure. Now, you cannot mix and match. You can't have some in as molarity and some as partial pressure. It's either all of one or all of the other. All right. But everything else is the same. Those calculations that we did for KEQ, KC, going to be exactly the same as what we're going to do for KP. The only difference is going to be the unit of the number that goes into that expression. All right. All right. So if all components of a reaction are gases, and then you can call KEQ KP. All right. The expression is written the same way, products over reactants. All right, and don't forget, if you have a coefficient in your balanced reaction, that becomes a power, all right, in that KEQ expression. Also, remember, no solids, no pure liquids, all right? The values included in the expression should be partial pressures. All right, and don't forget, still temperature dependent. All right, so the temperature should be listed. All right, now one kind of cool thing that you could do is convert between Kc, where you have molarities, and Kp, where you have partial pressures. All right, so the conversion between Kc and Kp. All right, so this is a formula where the equilibrium constant with pressure values is going to be equal to the equilibrium constant with molarity values times a correction factor. And this is going to be the gas law constant times whatever the temperature is raised to the delta N power. All right, so this is going to be our formula. All right, so R again is your gas law constant. So I tend to use 0.0821, and that unit there is ATMs times moles. Whoops, oh, that's wrong. Times liters divided by moles times Kelvin. All right, and so the presence of R is going to obviously set some of our units. One of them is going to be T. So this is our temperature, and it must be in kelvins. So don't forget, you need to add 273 to any Celsius measurement. All right, and then the new one is this delta N, and we know that delta means change in, so this is change in moles. So this is going to be moles of the products minus moles on the reactant side. All right. All right, so once we do that, we'll have that delta N and we can raise the power. These must be gases or aqueous. All right, do not include solids or liquids in that calculation. All right, now once you're finished with that conversion, because of R, you're going to get your partial pressures are going to come out of all of this as ATMs. All right. Okay, now obviously we could rearrange that formula and we could solve it for Kc, but we'll leave that in case we have to do it later. We'll do it then. All right, so let's try a couple problems. All right, so here at 1,000 degrees Kelvin, the equilibrium partial pressures for the reaction below are as stated. All right, so we've got CH4 at 0.2 ATMs. We've got H2S at 0.25 ATMs. We've got CS2 at 0.52 ATMs and H2 at 0.10 ATMs. So these are all our partial pressures. And then the question is asking, well, then what is Kp? All right, so we're going to start by writing our expression. Kp, remember, just like Kc or KEQs, products over reactants. So we'll start with CS2 times H2, and we need to raise that to the fourth power, divided by CH4 times H2S, and we'll need to square that. All right, so now we just need to plug everything in. So we have 0.52, all right, for CS2, 0.1 for H2. We'll need to raise that to the fourth power. Then we're going to divide that by 0.20 ATMs and 0.25 ATMs, and we'll need to square that. All right, so we put all of that into our calculator, and we find that the Kp value is 0.0042. All right, so what that tells me is for this particular reaction at equilibrium, we have more reactants present than products because our Kp value is less than 1. Okay, so that's just writing the expression and then plugging in to solve for the value. Okay, all right, for this problem, we've got a reaction, and we're told at 375 degrees Celsius what the KEQ is for equilibrium, if concentration values are known. All right, so the first step is, well, what is Kp? All right, so we need to convert. Kp equals Kc times R times T raised to the delta N. All right, we'll plug in Kc, 2.79 times 10 to the negative fifth. All right, we know that R is 0.0821, and that again is ATMs times liters divided by moles times Kelvin. And then we'll multiply that by the temperature. Now we have Celsius, so we need to add 273. All right, and that's going to give us a temperature of 648 K. All right, now for delta N, we look on the product side, I have 2 moles of gas, and then on the reactant side, I have 1 plus 3, 4 moles of gas. So the delta N for this reaction is negative 2 moles. All right, so we need to raise this to the negative 2 power. All right, so I plug all of that into my calculator, and I find that the Kp is going to be equal to 9.86 times 10 to the negative 9th. All right, now I can check my work slightly. All right, the Kc value was very small, which told me that at equilibrium I have more of my reactants present than my products. All right, my Kp value is also very small, which also tells me that I have more of my reactants present than my products. That should be the case. We should not go from a Kc to a Kp and find all of a sudden that products are favored. All right, that is not how it works. We're just converting units, really. All right, so make sure that you just check that and that your two answers, your Kc and your Kp, are both looking at the equilibrium in the same way. All right, part B. What is the partial pressure of ammonia if the partial pressures of H2 and N2 are as shown? All right, so now we're going to use that Kp value and solve for one of our components in the reaction. So we write our Kp expression for this reaction. So we've got, whoops. Oh, I realized I did something wrong up there. You should be writing this as partial pressure of NH3. All right, and that's going to need to be squared, divided by the partial pressure of N2 times the partial pressure of H2 cubed. All right, let me fix this. All right, you guys see what I did up here? I listed all of these as concentrations, All right, that's one thing to keep in mind is these are partial pressures. So CS2 times the partial pressure of H2, and this needs to go up to the fourth power. Down here, the partial pressure of CH4 and the partial pressure of H2S squared. Sorry about that. Yeah, we should list them as partial pressures. Okay, so I come back down. I know that Kp is 9.86 times 10 to the negative ninth because I figured that out in part A. All right, my unknown is going to be the partial pressure of NH3. So I'm going to leave that as is. And then down below, I have 2.17 atmospheres of the nitrogen and then 1.24 atmospheres of the hydrogen cubed. All right, so I'm going to do my mathematics on the bottom, and then I'm going to multiply that over to the 9.86 times 10 to the negative ninth, and then I'm going to take the square root of both sides. All right, but just so you can see what that's going to look like, 1.24, I'm going to raise that to the third power, and then going to multiply that by 2.17. All right, and then I'm going to multiply that by 9.86 times 10 to the negative ninth. All right, so I'm going to get 4.08 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, negative 8. That's going to be equal to the partial pressure of NH3 squared. So then I'm going to take the square root of both sides, and I'm going to find that the partial pressure of NH3 within this system is 2.10 times 10 to the negative fourth, and that's going to be units of atmospheres because of that conversion that we did up in part A. All right, so I asked myself, is this reasonable? All right, well, my Kp value tells me that there should be way more reactants present than products. And if I look, I have 2.17 atmospheres and 1.24 atmospheres of my reactants and a very small amount of product. So this is a reasonable answer to this question. So make sure you always check that your answer is reasonable when you're finished. All right, one last problem. All right, for the reaction below, if Kp is 50.5 and the initial pressures of Hi is this, H2 is this, and I2 is this, what are the equilibrium pressures? So we're looking for the equilibrium values for all substances. All right, so there's a couple things going on here. All right, first, we have a Kp value and we have some concentrations, but we're not really sure which direction the reaction is running at this point. So what we're going to need to do first is calculate Q, all right, because Q is going to tell us, compared to Kp, whether the system is producing more reactants or producing more products at this particular set of partial pressure values, all right? We're going to calculate Q to determine reaction direction, all right? And with that, we're going to set up our rice chart with change row showing this direction. All right, so in other words, we need to know where we should be adding stuff in and where we should be removing it. We cannot make the assumption that we're just going towards the products. You got to check. All right, so we're going to start with our Q calculation. All right, so we write our expression for Q. So we've got the partial pressure of Hi squared divided by the partial pressure of H2 times the partial pressure of I2. All right, so you can see, just like our Kp expression, our Qp expression can use those partial pressures. All right, so we plug in what we've got, 0.975 atms squared divided by 0.105 atms for hydrogen and 0.105 atms for iodine. So we plug those values in and we get 86.2 for Q. All right, so then we look, well, Kp is 50.5, so Q is greater than Kp. All right, so what that tells me is reaction moving to the left. All right, we need to get back to equilibrium. So we've overshot the equilibrium amounts, and we need to use up some of those products to form reactants to get to equilibrium. All right, so that's going to show up in our rice chart. All right, so let's start by writing our reaction. H2 gas plus I2 gas forms 2HI gas. All right, now according to this information, the reaction is running this way. All right, so we put in our initial amounts, 105 ATMs, 105 ATMs, 0.975 ATMs. And the change row is where we're going to see this Q versus KP information. So we are going to lose 2x of HI, and we are going to gain X and gain X for our two reactants to indicate that we recognize that the reaction is in fact moving towards the left. All right, so 0.105 plus X, 0.105 plus X, and then 0.975 minus 2X. Okay. All right, so where am I going to put this? I'm going to leave myself a little bit of room up there. I think I'll do it down here. All right, so Kp is going to be equal to the partial pressure of Hi squared divided by the partial pressure of H2 and the partial pressure of I2. All right, we know that Kp is 50.5. All right, so up here we're going to put 0.975 minus 2x squared. Now below, we're going to have 0.105 plus x times 0.105 plus x, but we could rewrite that as 0.105 plus x squared. So we've got a square on the top and the bottom. So what we can do is square root both sides. So that's going to take care of those, which is going to make our math a lot easier. All right, so the square root of 50.5 is 7.11. That's going to be equal to 0.975 minus 2x divided by 0.105 plus x. So we need to multiply the 0.105 plus x to both sides. We end up 0.746 plus 7.11x equal to 0.975 minus 2x. All right, then we need to isolate x. All right, we're going to get 9.11x equal to 0.229. And then we're going to divide both sides by 9.11. So we're going to get 0.0251 ATMs. And this is the change. All right, so we need to go back up to our ice chart, and we need to incorporate that change in. All right, so 0.105 plus 0.0251. All right, so we're going to end up with 0.130 ATMs for each of these, right? And then this will become 0.925 ATMs because we'll double X and then subtract it out, all right? So our equilibrium partial pressures are these three values, all right? If you want to check, just plug them into your Kp expression. So 0.925 squared divided by 0.13 divided by 0.13, and we get 50.6. All right, so that gets us right back to that Kp value, so we know that we have done it correctly. All right, so when in doubt, make sure you check that work. Okay, all right, so as you can tell, the Kp version of the equilibrium expression is exactly the same as KEQ or KC, except we use partial pressure values. All right, there is a way to convert from KC to KP using the formula shown. Just don't forget, when you get those partial pressures out after that conversion, the units are going to be in ATMs if you use this version of the gas law constant, the 0.0821. There are other versions of the gas law constant that have kilopascals in them. If you want to use one of those, or torr, or millimeters of mercury, you may. Your partial pressure values will come out with that particular unit for pressure. Okay?